You're listening to Let's Talk Creation with Todd Wood and Paul Garner, the creation show where we learn, grow, and worship.
Welcome back to another episode of Let's Talk Creation with Todd and Paul. I am Todd Wood.
And I'm Paul Garner.
And I want to start off the episode, as we usually do, reminding you that we really appreciate all of the support that you do. This is an important podcast and expensive one to produce. We appreciate your donations. You can visit our website, letstalkcreation.org, to find out how you can sponsor episodes or how you can just make a contribution to the show. And we very much appreciate that. We also remind you at the top of the episode to like and subscribe and click that notification bell if you're on YouTube. Leave us a review if you're on some other platform. Share our episodes, share them with your friends, share them with your family, share them with your enemies. Do whatever you can. Help us out. We really appreciate the opportunity to spread our audience and grow our influence. So thank you so much for that.
Yep, we do indeed.
All right, Paul. Today,
Yeah,
we've got a good topic here.
we have. Yeah, this is really interesting.
So you know, Paul, that by training, my PhD is in chemistry, a biochemistry to be specific. And I, as a chemist, we like a good chemistry joke from time to time. And today's episode is related to this one that I see floating around the internet a lot. It is a version of the periodic table called Can I Lick It? There's the actual periodic table there with different elements colored in for Can I Lick It? Different categories. Sure, it's probably fine. Maybe not a good idea. You really shouldn't. And please reconsider. I might quibble with the position of some of these elements. I think fluorine, for example, is far more dangerous than, say, mercury.
Right.
I don't know. It's bad stuff. Anywho, so this episode is all about nasty chemicals and specifically dangerous chemicals. So I thought I'd share that little thing with you just to get us going here. And so our topic today is the chemistry of the flood. How do we account for toxic chemicals? And it's not a topic that we hear about a lot. It's not a common criticism, nor is it a common, rebuttal, I guess. But it is really important because, at least in theory, the flood could kick up a lot of the elements that you should never, ever lick. So, that's probably bad. So to help us think through this issue, we have our special guest here, Aaron Hutchison. He is a chemist at Cedarville University. Welcome, Aaron.
Hi, glad to be here. Hello, Aaron.
He has a bachelor's degree in chemistry. He has a PhD in chemistry. He is a professor of chemistry at Cedarville. He is a chemist through and through. When he is not doing chemistry, he is serving on the board, the organizing committee for the International Conference on Creationism. And he is also, in the past, served as a senior pastor and is now a lay elder. So he is a busy guy, and he has done a lot of research on this episode's topic, and that is toxic elements in the flood. So we're going to focus on that, and we will definitely put links to his technical articles in the show notes. If you're interested in reading technical chemistry stuff, feel free to look that up. If you want to, fact check anything that we say here, we encourage you to do that. We are good Bereans here. Don't just take our word for it. Look these things up and make sure that we're giving you the straight story. Okay, so let me just set the stage here. Creationists often think about the the flood and Earth history in ways that are kind of like accelerated versions of otherwise slow processes. So like erosion, for example, instead of a little bit of water and a whole lot of time, creationists imagine it's a lot of water in a very short amount of time. So there's an intense amount of energy very quickly that does the work that would take a little bit of energy a very long time to do. Same deal for, making rock layers and fossils and so forth. Instead of a little bit of sedimentation over a long period of time, we got a lot of sedimentation in a little bit of time. And when we do that kind of thing, it does raise some interesting questions and problems related to the flood. One question that we've covered in several different episodes is the heat problem. That much movement of continents, that much radioactive decay is going to generate, at least in theory, it should generate a lot of heat. And so where does that heat go? And how do we not melt the Earth and so forth? There are other questions as well, other questions that don't quite get such spotlight as the heat problem, but they are, I think, relevant. And as I mentioned, it's all about the toxic contamination of the floodwater. So Aaron, can you walk us through what exactly are the problem? What is the problem? What is the problem with the toxic flood?
Sure. So the big issue here is we do have elements in the rock layers that are extremely poisonous to man, and in some cases to almost all living things. Two in particular that are especially bad are arsenic and mercury. The arsenic, the WHO drinking water standard is 10 part per billion. There's places on Earth right now where you're getting up to 50 part per billion or higher in the surface waters people are drinking, just due to the natural geochemistry of the environment they live in. So you magnify that with a flood, you could get a lot of arsenic in the water. The mercury is also out there. Mercury in general is actually considered a little more toxic. The WHO level for it's 6 part per billion rather than 10. It can be extremely dangerous. Both of them can kill you. What you would see is a little different between the two. Arsenic, if somebody gets a really big dose, think a lot of British mysteries from the early to mid 1900s when they were using arsenic to kill moles. And so anyone could walk down to their hardware store and buy arsenic, which means arsenic got used to remove impediments other than just moles. But a dose of arsenic in the milligrams per kilogram body weight range can often be immediately fatal within a course of a day. Person, it would cause extreme damage to the stomach and just a whole digestive system and cause internal bleeding. Person would die.
Wow.
Then the lower level, that above 10 part per billion over time, that's not what shows up in the mystery novels, but what actually showed up in the real world now. If a person's getting that sort of exposure to arsenic over an extended period, what you would expect to see is a much higher increase in cancer. And there's things called Blackfoot disease, that people develop these black lesions on their hands and feet. They're extremely painful. Generally, if that's happening, you've also got high enough dose, you've got an extremely elevated risk of cancer. And so that's what long-term effects to relatively small amounts for arsenic will do. For mercury, it primarily attacks the nervous system. Probably a lot of your ears are aware, the whole phrase mad as a hatter came from using mercury to remove lint when making hats, the exposure to it often will manifest as neurological problems. That you'll have people getting, developing like twitches, developing trouble thinking, behaving irrationally, and then it can end in death. That with mercury, there's multiple forms going through the environment. The big concern is the form you'd find in rocks would be usually mercury 2+. But in the environment, if that gets into the water, that's fairly dangerous. But there's actually some bacteria that can form what's called methylmercury, adding a carbon to it. That is exponentially more dangerous not because the chemistry is any worse, but because it can, the body doesn't really recognize it as a metal. It treats it like an organic molecule, and so it can potentially cross the blood-brain barrier. Many of the natural defenses of the body against metal poisonings not getting triggered by methylmercury. When I was in graduate school, doing research on mercury, in fact, there was a case, I believe it was at Dartmouth, where a graduate student preparing a sample for analysis accidentally got 1 or 2 drops of a methylmercury on her glove, and enough soaked through the glove in the time it took her to take off the glove that she received a lethal dose and died. That it's that toxic.
Wow.
And it also accumulates in marine organisms. So especially with the mercury, if you get mercury at a higher concentration in water, then a small but non-negligible percentage of that's going to get converted into methylmercury. The methylmercury will be eaten by small organisms, they get eaten by smaller fish, they get eaten by bigger fish, but all up the chain, it's never getting excreted in large amounts by the organisms. The more they eat, the more they accumulate in their muscle tissue. What we can eat are the fish at the top of the food chain. And so by the time it gets up there, it can be several orders of magnitude more concentrated in the muscles of the fish at the top of the food chain than it was in the actual water. And so there's a definite danger there if you get that accumulating in your water.
So, wow. Yeah, that's pretty bad. That sounds really bad. So certain. Now you mentioned this, and I think this is a terribly important thing that we ought to think about here for a second. You mentioned different forms of mercury. So you mentioned that there's methylmercury, which is worse than normal mercury, and I assume there are different forms of arsenic as well. So not all elements are equally destructive in different forms. There are ways of making certain elements more dangerous than they otherwise would be. Is that right?
Yes. The form matters a great deal. So for arsenic, there's multiple possible forms. There's 2 common ones, are arsenic 3+ and arsenic 5+. They are both toxic, but how soluble they're going to be, what form they're going to show up in, will differ significantly based on which type it is. Mercury, you have 3 common. You've got the mercury 0, that's your liquid. That's what we are familiar with in thermometers and such. The liquid mercury, it's by far the least toxic. You've got mercury 2+, and you've got mercury, methylmercury, which is a version of mercury 2+, but it's got the methyl on it.
Yeah, okay. That makes sense. Because I remember my grandpa telling me about playing with mercury as a kid. He would rub it onto coins and turn them all shiny silver again. And he did not seem mentally deficient to me, but maybe he was not using the same form of mercury. So So what does this mean then for the flood itself? I mean, I imagine, when I think about the ocean, it's one thing that I notice about it is that it's very large. And I imagine, and maybe I'm naive about this, but I would imagine that, you could dilute a lot of toxins just by virtue of there is a large volume of water that they're going into. So I guess the question is, even if you put some really awful, terrible things into the water, then how bad is it when you think about the flood itself, the flood writ large, if you will?
Mm-hmm. Sure. So I think the issue there we have to think about is what's going to be the chemistry of the elements in the flood. That you're right, the sheer amount of water means the concentration is going to be small. You could get a lot of mercury arsenic dissolved in the amount of water you're talking about without ever getting a real high concentration. The question is, especially during the flood, almost all the organisms are dying, which would to a certain extent help with that whole issue of magnification up a food chain. Your food chains are being somewhat disrupted. But the issue you've got, I think we really have to worry about is what's going on in the water as the floodwaters recede and we start settling back into the post-flood world. If the flood released a tremendous amount of these toxins, and the idea would be if today they're found in rock, if you're doing a flood, massive amounts of rock is being eroded. If huge amounts of this got released and nothing removed them, then they're still there. And as you start settling back in after the flood, they're available to be in drinking water and to start working their way up a food chain. And the danger there would be, you wouldn't have it high enough to be an immediate lethal dose of anything.
Right.
But if the waters are significantly contaminated in it, then, if no one, his ancestors are eating seafood, they're picking up mercury. If they're drinking the water year after year, they're accumulating a very dangerous dose of arsenic. That would be where a lot of the concern would be. That I have seen when critics are, which there's not many that use this, that actually I think I'm the person that pointed out arsenic needed to be thought about as a problem. Craig's had, the history there was a Craig hit on mercury. I looked at and my immediate thought was, I can answer mercury. Mercury's not a problem. I think arsenic's a problem. So I worked into that too. But when the Craigs are putting this out, what they're taking is just the total amount that would be released. And we're not thinking about what chemistry would actually happen with it. Right. If that total amount is still staying in the water when we try to reestablish life on Earth, we do have a problem. That's not going to be good for trying to reestablish life.
Yeah, especially if you've got, I would imagine fishing would be a good source of food for a lot of the people after the flood. And if you've got a lot of mercury building up, then that's a bad thing. Where do mercury and arsenic come from in the environment? I guess God made them, but how do they where is the main source of these elements that they leach into certain water supplies? Where do they come from?
The immediate, kind of point source in the environment today tends to be volcanoes or hydrothermal fluids coming up. So they're concentrated subsurface, and the sorts of things that are pushing fluids through the rock layers up to the surface of the earth is where you're getting both of them enriched. So this is especially obvious in the case of arsenic. If you think about Yellowstone with all those geysers, many times there's significant deposits of arsenic around those. So hydrothermal fluids, but it's also the case in mercury, that the places in the world where we see really elevated amounts of mercury that surely looks to have been the result of hydrothermal fluids coming up and depositing it. We see major enrichments in mercury from volcanoes. In fact, you can almost track when there was big volcanic eruptions around the world by looking at mercury concentrations in ice cores. For recent enough history that we can track the ice cores, you can see the spike in mercury concentration around the world when there were major volcanic eruptions. Those would be your big sources.
Wow. Okay. Well, I mean, that just sort of magnifies the problem then, doesn't it, Paul? Because
Yeah.
the
flood is going to be it's a tectonic catastrophe, and there are going to be lots of hydrothermal fluids kind of venting into the global ocean, and lots of volcanic activity as well. So that kind of raises the question. I mean, a kind of related question, going back to what Todd was just saying, what's the source of these things? Ultimately, of course, God created the elements. But, why did God create toxic elements like arsenic and mercury in the first place? I mean, did they also have some sort of beneficial uses as well as the potential problems?
They do. Mercury especially has had many good uses. Mercury is actually the first antibiotic man knew. It would be very, it was been used medicinally. It's been used as a catalyst for some chemical reactions. Obviously, very important for measuring pressure and temperature. Mercury has just been extremely useful, man, for a number of things. That's part of the way we've got mercury in the environment. One source is pollution from people using it, for in many cases, very legitimate uses. It's also important for mining, actually. Arsenic has less good uses, but there are some. You can do some pigments with arsenic. You can make poisons, which, there are legitimate uses for poisons in a fallen world. It's been used that way. Theoretically, I think you could do some antibiotic stuff with it, although getting the dosing, no one today would suggest that. As I said, historically, it's been a pesticide. I think there has been at least some consideration. I know mercury they've used medicinally. I think arsenic, but I won't swear on that one. I'd have to look that up. So, there are legitimate uses. This may be getting ahead of the questions, I do think where they were in the environment was probably different pre-flood than is post-flood.
Yes. Yeah, I mean, that was one of the things I was going to say. I guess as a result of the flood itself, probably there's more of these toxic elements near the surface than perhaps there was in the pre-flood world, in the original created world anyway.
Mm-hmm. I think so.
Yeah. So that kind of brings us back to the problem, which is flood.
Do we have a problem? I guess that's the big question. Now I've done a little bit of my homework here, reading over your papers, and I know that there's a really key question in your research, and that question is about a chemistry concept called solubility. So, I know what that is, and as soon as I read the word solubility, I thought, oh yeah, that's going to take care of a lot of this problem. So, maybe you could walk us through the question of solubility for your chemistry 101 lecture on solubility. Can you boil that down here and help us understand it?
Sure. So we've been talking about this as if we're talking about just mercury 2+, maybe just arsenic 5+, are most water-soluble forms by themselves. But they're never by themselves. In nature, when you've got a metal, something with a positive charge, you've always got something with a negative charge with it. And depending what is with it, everything does not dissolve in water equally well. So like table salt is sodium chloride. It dissolves very, very well in water. If you replace the sodium with silver, So I have silver chloride. That does not dissolve well in water. It makes a white solid and sits on the bottom of whatever you had it in. And that's true, any chemical compound we talk about, vast majority, especially the sorts of things that make up minerals and rocks, that they're not all forms of them will dissolve equally well in water. It depends on what positive and negative charges are together, what compounds are combining. So a big issue here is how soluble are these things. And many of the things we're talking about, this is all our starting point on this is rocks. Rocks obviously are not hugely soluble in water. That's why we don't lose all of our rocks every time it rains, right?
That's right.
Our rocks are not like salt. And so the actual likelihood of these things being dissolved in the water depends on what it's with and how soluble they are. Kind of a little excursion. I think among creationists, there's room for us to think more about this, because every mineral out there is a chemical compound. Most of those, actually, if you go into the chemical literature, we've done studies and published things on their solubility. Something really interesting I saw in some research I was doing a few years ago. I was talking to a colleague about the history of a rock layer, set of rock layers. I think it was like a little over a kilometer deep in the Canadian Rockies. I was just looking at the minerals there. They are sitting on top of each other in the exact order of their solubility in a chemistry textbook. That if you just mixed two solutions of water with the elements that make up those minerals together, they would form solids and they would layer themselves in the exact same exact same pattern I saw in those rock layers. And the whole process in my lab would take less than a minute. That now you're talking about the heat problem earlier, under the heat and pressure that probably would be going under the flood, it might take a little longer, it might take a few minutes. But so solubility is a huge issue, and that's the key issue for these poisonous elements. Are they actually dissolving in the water?
Right. If they're not dissolving in the water, they're really not getting, it's much more difficult to get them into a biological organism to kill it, right? It's much harder to do that. Okay. Yeah. And you mentioned silver chloride. That's, as a chemist, that's one of my favorite demos is mixing silver nitrate and any solution with a chloride in it. And it looks all clear and fine. And then suddenly you get this big cloud of white stuff. And that's solubility, folks. That's if you've ever seen that funny demonstration by your chemistry teacher, that's what he was trying to explain to you. There are things that don't dissolve in water very well at all. So, and Paul, I think you should probably look into this whole mineral solubility question. You with all your free time.
That sounds really interesting. I'll be intrigued to know more about that.
Yeah, that's very curious there. Okay, so
there's lots of geochemical issues in the flood, isn't there? And you mentioned salt. Of course, we do have rock salt deposits as well, and that's another whole area that would be a really interesting one to talk about sometime.
Yes, yeah, that would. I agree. Geochemistry. Yeah, there's a lot about geochemistry that I find really interesting. There's a lot of weird minerals that just seem so very sensitive to chemical deposition. But this is about the toxic flood, not about geochemistry. We'll save geochemistry for another episode. Because we're going to talk a long time about that, I'm sure. Okay, so solubility. You got your different forms. So we mentioned the different chemical forms of the different elements. We mentioned that the different chemicals have different solubilities. Some of them just don't get into the water, which makes them much harder to cause damage in living systems if they don't actually mobilize in the water. So, okay, so let's connect that then to what we're talking about with mercury and arsenic. So maybe we should start with the mercury question, which you said was the easier question. So why do you think that's the easier? What is it about the solubility of mercury that makes you think that that's an easier question?
Sure. So the reason I think that's an easier question is the mercury, we're talking a lot of this probably coming up through hydrothermal fluids during the flood. Hydrothermal fluids can be rich in mercury. They're also very often rich in sulfur, and many times in the sulfur 2- form. The sulfur 2- has an incredibly great love for mercury. In fact, the Latin name for organic sulfur compounds is mercaptans, for mercury capturing. That was how the Romans literally classified these compounds. They're the things that will jump on mercury.
Interesting.
So what could be happening in hydrothermal fluid, because it's so extremely hot and under very high pressure, you can have the fluid coming up and you've got mercury and sulfur both dissolved because of that temperature. But as that starts moving into cooler surface waters, it's going to cool down. And as it cools down, one of the first things going to happen is you'll precipitate mercury sulfide, cinnabar, in various forms. That happens, we've seen that happen in other places around the world. And so that will be deposited. You'll have mercury sulfide on, around the deposit. Now, if the deposit is sitting just like on the bottom of a seafloor, that's still not great because the mercury's there, the water's above it. You're going to have some mercury dissolving, some precipitating, becoming solid. You'd still be getting more mercury than you want in the water. But this is the flood. It's not just kind of passively sitting on a chemically, physically stable seafloor. You're laying down rock layers on top of it rapidly. And so the result would be a high proportion, maybe like 90% of the mercury coming out of hydrothermal fluid is going to precipitate as mercury sulfide as soon as it cools down, and then is going to get buried. In fact, we've got a few spots in the geologic record where we've got these giant deposits of mercury sulfide, pretty clearly formed from hydrothermal fluids, I suspect formed during the flood. I've done some research on this. I haven't been able to come to a definite conclusion why. There's a couple spots, one in Romania, one in Spain, where you've got these really high. You clearly had this just super enriched mercury fluid coming up and precipitating mercury sulfide. And I'll admit, I haven't been able to figure out why that spot versus somewhere else, but I can see in the geologic record where that happened. And, during a flood, they'll be burying it. A lot of it's simply not going to ever get into the water. Likewise, to the extent, I think most of the mercury we see in the geologic column today was actually moved from deep in the earth during the flood. But you would have, anything on the surface during the flood is likely, a lot of it's going to be getting precipitated by sulfides. Some other things can do it too, but sulfides are your big one. During the course of the flood, it becomes a solid, it gets buried. And if it gets buried, it's not nearly as available to be a threat to organisms.
So the vast majority of mercury is coming out of the ground as contamination is almost immediately precipitating out.
Mm-hmm.
It's just not soluble when it reacts with sulfide.
Right.
Makes sense.
And then,
So the sulfide, help me understand here. I've been to Yellowstone. I've walked among the geysers there. They stink like rotten eggs. Is that the sulfur you're talking about?
That it is.
Yeah.
That thing is a gas called hydrogen sulfide.
Okay.
And that'll react. If you were bubbling that through a solution of mercury, you'd see solid mercury sulfide forming at the bottom.
Wow. Okay. Well, that makes sense then. I mean, that fits with what I know about steamy hydrothermal geysers.
Yeah. The other thing at the flood that would probably be tying up a lot of mercury is actually all the dead organisms. Because there's sulfur groups in or decaying organic material, mercury tends to accumulate on decaying organic material. There's a lot of decaying organic material in the flood. I mean, this is why I think we tend to see mercury enriched in some of the black shale levels. That it's so the mercury that's not immediately precipitating when it comes out hydrothermal, because you gauge some into the water through the volcanoes, for example. Awful lot of that's going to be getting caught up in just all that dead organisms, and it's getting buried with them.
Wow. I mean, that's kind of remarkable when you think about it. It's almost like it was planned that way to be able to precipitate out and not cause future harm. Okay, well, that's mercury. So let's talk about the hard one, the arsenic. So what's the deal with the solubility of the arsenic compounds? Yeah.
The arsenic, in general, is more soluble than the mercury, which makes it tricky. It also forms the mercury we talk about, you got like the 2+. Arsenic, what's self-positive, it will bond with some oxygens and form a compound that's actually net negative. And that's often much harder to get out of water than something that's positive. So arsenic's a bigger problem, but I think we can still understand it if we kind of trace through the route it would take from the flood. So if you start with hydrothermal fluid coming up during the flood, the arsenic in that fluid's initially probably going to be in the 3+ form. And that's the form that is most likely to combine with sulfur, just like the mercury did. So the initial thing that happens when the arsenic comes out, it's pretty similar to what would happen with the mercury. Initially, it will form arsenic sulfides. The problem is, if that arsenic sulfide comes in contact with oxygen or oxygen-rich waters, it converts from arsenic 3+ to arsenic 5+ and redissolves in the water.
All right.
And so you get the arsenic going back into the water. However, this is where this gets really interesting. While that's happening, you're also likely to be getting iron dissolved in the water. Iron's much more abundant than arsenic or mercury, either one, in our Earth. And iron reacts with oxygen. If you've got oxygen water, iron reacts with oxygen and forms iron oxides. We're familiar with them as rust. Arsenic oxides arsenic 5 oxides have a very high tendency to accumulate on particles of iron oxides. And when the iron oxide becomes solid and falls out of the water, it can pull the arsenic oxide with it. And so that it can go back into the water, but then you've got a defense in that the iron, if you've got iron coming into the water also and reacting with the oxygen, the same oxygen that released the arsenic can now create a deposit that will recapture it. And so the arsenic will come back out of the water. However, if you lose the oxygen content of the water above it, then the process reverses. You go back to the arsenic 3 and it becomes soluble again. And this can go in Southeast Asia, where we've got our biggest problems with arsenic contamination in drinking water. There's a lot of debate among chemists about the exact order things are happening in and the exact process, but it's pretty clear it's a seasonal thing. That what you're doing is seeing changes in the oxygen content of the water, And so you've got this whole cycle where the arsenic becomes soluble, it's insoluble, it's soluble, it's insoluble. And so you're getting these seasonal bursts of arsenic going through based on the oxygen content of the water.
Wow.
Mm-hmm. So here's how I...
No, yeah, go on.
Yeah, so here's how I think that worked out in the flood.
Yeah.
Think what happened was we had a lot of arsenic coming up in hydrothermal fluids, initially forming arsenic sulfides, many of which got buried initially. However, we had a burst of mountain building in probably the last stages of the flood. There's debate among creationists, is this immediately post-flood or late flood? But we've got some mountain building where you've got mountains like the Himalayas and the Andes coming up. I think when those rose, there's a great deal of erosion. And that erosion exposed those arsenic sulfides to oxygen and oxygenated water. They became more soluble, but it also released iron. And what wound up happening was you transferred them from up on the mountain down into the basins of sedimentary rock below the mountain, where they got trapped, associated with iron oxides. That's where they're sitting today, and that's why your greatest likelihood of getting arsenic contamination of groundwater is in the sedimentary basins in the shadows of those last mountain ranges to rise. But that's where we find the arsenic near the surface today. And I think that's how it got there. It was initially the arsenic 3, when the mountains rose and you had erosion off the mountains, that converted to arsenic 5 and moved it down into the sedimentary basin. It was trapped in the iron oxides there, but it's now close enough to the surface that potentially changes in the oxygen content of the water can free it. And so now it's a danger that was never a danger before the flood.
So are there deposits of arsenic that you can point to in the fossil record? Do you know?
Some of I believe there are some spots, a lot of it is almost always in these sedimentary basins of the more recent mountain layers. There are some places where it's found in just hydrothermal systems, and usually what's in the sedimentary basins, the arsenic 5, what's in the hydrothermal systems, including some buried hydrothermal systems, that's your arsenic 3 many times. It's not, obviously, where you have one, you have the other. It's not 100%.
Right.
But that's where you get more of it. You sometimes get some of that showing up in coal. So there are some enriched spots in the sedimentary record. It's not as pronounced as the Mercury. The Mercury's got a few real concentrated spots.
Right.
The arsenic, it's not quite so much, but there are some.
Wow. So then I guess question is, do you think these mechanisms take care of the problem that you've posed? Is enough? Okay. There's a lot of mercury coming up into a lot of mercury and arsenic coming up into the environment, both from the grinding of the continents around and from the tectonic, eruptions of volcanoes and whatnot. So there would be a lot of this stuff coming up. And you've described a number of mechanisms here that would create essentially insoluble or poorly soluble versions of these toxic elements that could potentially sequester the elements into a form that is not out there killing people, which I thoroughly like. Let's do that. Let's sequester all these toxic elements. Okay, so is that enough in terms of the magnitude of the problem? We've got all this stuff coming up. Is there enough there to take care of the problem altogether then?
Yes.
Okay.
There. So your listeners don't want to hear me do a bunch of math.
Well, probably.
So my technical paper on Mercury, I actually did some calculations on total amount of mercury probably in the geologic record, as best we can estimate it, how much would become soluble, what levels of sulfur would we have. I actually did the math on it and demonstrated it should never have reached a truly dangerous concentration in the floodwaters. That you would not expect that. The arsenic, I think the issue is kind of the history of the arsenic. The problem would have been worse if the environment undergoing the flood was the environment we have right now. So if those arsenic-rich sedimentary basins were sitting there pre-flood, those things would have been a huge release of arsenic.
Yeah.
I don't think they were there pre-flood. I think they were made by the flood. That prior to God's judgment, I don't think we had that much arsenic in the arsenic oxide soluble form up at the surface where it was getting into groundwater. I think it was the flood that did it in those two stages. And if you go with that model, you don't really get it at the surface in the level where it would be dangerous till the very end. It's right when you're forming those sedimentary basins in the last burst of mountain building that's the final kick that pushes it up to the surface. And so you shouldn't have got a huge concentration in most of the groundwater.
Wow. Well, that's good to know.
Interesting.
At least the flood's not going to poison us. It may drown us, but it won't poison us. Yeah. Okay. Well, that has been a very complicated subject. I am sure we've lost some people in the audience, but the basic story that you've told me, there are these toxic elements that could produce very bad results if they got too concentrated in the environment during and after the flood, but that there are ways that we can understand this that makes it not a problem, at least in terms of ongoing toxicity. The mercury is generally going to precipitate. Arsenic problem generally comes after the flood at the formation of sedimentary basins. It's not something that's happening in the flood. So when you talk about all the things that die in the flood, I think it's important to remember that there's a lot of stuff that survives as well, right? There are plants that survive. There are sea creatures that survive, aquatic creatures that survive.
Mm-hmm.
So this would be especially important for them because they are not sequestered away in the ark. They are out there experiencing the water themselves. And so this is not just a theoretical problem of what happens when Noah gets off the ark and there's arsenic in his cup of water. It's, how does anything survive the flood at all? So this is very important to understand that it seems problematic, which is a lot of what I find in creationism. It seems like that couldn't possibly happen until you actually sit down and do the calculations in the math and think through the problem and realize, oh, well, maybe that's not such a big problem as we have imagined. All right. Well, I hope everybody understood that. Did I get that summary correct?
Yes, that's an excellent summary of it.
Well, I don't know that it's an understandable summary, but at least it's a summary. So before we let you go, we have to talk about the International Conference on Creationism. As you know, Paul and I, big fans of the ICC. We presented papers there last time in 23. Most of our audience is probably familiar with what ICC is, but just in case there are people out there who have never heard of this, can you describe what the International Conference on Creationism is? What is it?
Sure. So the ICC is a conference. Actually, we're kind of slowly becoming a family of conferences. We've bridged down to more than one. We're a conference dedicated to giving an opportunity to present original positive creation research. Our prime focus is not let's bash the evolutionists. Some of that happens, but our the goal is actually presenting positive scientific models. Let's look at and say, okay, with our understanding of what happened with creation, the flood, what should this look like? And what does our scientific data actually say? And how do these things fit together? The research is always peer-reviewed, scientific research. The ICC is independent of any of the major creationist organizations. We work with them. We work with ICR and AIG and other organizations, but we're independent of all the organizations. We are almost a neutral ground for people to come present their research. We do our major conference every 4 years. That's what we're running right now. And then we're looking to start, we did the first one last spring, something called the New Scholars Conference on the second year in between the main conference. This would be a smaller conference geared towards, as the name says, new scholars. People that are just getting started in creation research, or especially trying to make it attractive to college students there, presenting smaller presentations, not the full ICC research papers. And but an opportunity for them to get started.
Yeah.
Full ICC, we have different types of presentations, but the heart of it is people presenting very rigorously reviewed scientific papers covering the various topics in creation.
All right. So that is ICC. Paul and I were there in 23. Paul, were you involved as an editor? It seemed like you were one of the editors. Is that right?
I was this last time. I was one of the editors. And yes, you're quite right. The papers are peer reviewed. And I was sort of involved in handling some of those papers in the geology section of the conference. Yeah.
And we had a good time at ICC 23.
We had a great time. We always have a great time. We even had a booth for the podcast at the last ICC, which was fun. And I think one of the great strengths of ICC, and it was something Aaron just said, is the way that it provides a kind of, it's a unifying force in creationism. It brings together creationists from all organizations and none to present their research every 4 years. And I think that's one of the real values and strengths of ICC.
Yep, I agree. And it's been going on since the 80s. So we're approaching the 10th ICC here very soon. And so that's pretty exciting. I don't know that they really imagined the 10th conference back when it was launched in the early 80s, but here we are.
Yeah.
The next ICC is set for July 13 through 16, 2027. That is a little bit less than 2 years away. Sounds like a long time, but as we know, as adult people, time flies, right? So what is the timeline looking like? Can you walk us through the basic timeline of submitting to ICC?
Sure. In the relatively near future, probably the next few months, there should be emails going out to everyone on our email list, and we'll try to get advertisements out through the creationist organizations as well, soliciting proposals. And so the first step, especially for the main research papers, as I said, we do have different levels of presentations. But for the big research papers, we have people submit a proposal describing, why their work's important for creation, what they're actually planning to do or have done, maybe giving us some preliminary results, preliminary list of references. So, and those are by the editors of ICC. We've got a group of us that will go through those proposals, and we'll look at them. Some cases they'll say, this is great, just go with it. Some cases will say, this really isn't what we were looking for, we're not going forward with this proposal. many cases, what we're going to go back to the author and say, okay, you've got a really good idea here. We think you should, you need to pursue this, or you should do this, or you should change your focus a little this way. One advantage of this is it's all the editors look at those proposals will actually be creation researchers, people that are active in doing research themselves. And so we'll go through and provide some feedback to the people submitting the proposals. There'll be a chance for folks to come back to us. There'll be some interaction. Once the proposals are accepted, then those have been accepted, the authors start to work on the actual papers. And all through next year, so this time next year, I would expect we're going to begin the first drafts of papers in. And we'll be reviewing those. There'll be a group of editors under John Whitmore's our senior editor. But then there's a group of editors. I'm usually like an editor for chemistry and wind up helping with geochemistry stuff and such. Because we don't get as many chemistry papers as we need to. But, we need more chemistry papers. I'm the editor on chemistry. I can't be the only one submitting chemistry. Yes, that's all right. But so I usually will probably wind up helping with some others. And, Paul will probably be helping in geology. And then, so we get various people, and then we'll farm out, the editors look at the papers and we'll send them off to expert reviewers. People like you, Todd, actually. And, we've had all sorts of people that we have, usually a paper has 2 to 3 expert reviewers plus the editor does a review in some cases, depending on whether the editor is comfortable, they have the expertise to serve as a reviewer or not. We always want, we're shooting generally for 3 reviews on each one. We feed those comments back to the authors, and they make changes and responses, and we go through, all through next year, we'll be going through that process. I know the last when I was working with authors on papers up to about a month before the conference, as we get as we work with them to make each paper and presentation the best we can get. And then when the actual conference occurs, there will be time slots for people to then present their research. The papers will also be written up in journal format and published through Cedarville University's library. There'll be an electronic form of those. We'll probably have abstracts for some of the other presentations and such published there. But the full papers will be published, but then the authors also present the work at the conference.
And
so it's a very...
the conference I was going to say it's massive. If you have not been to an ICC, it's something to see, really. Hundreds of people there. And as you say, neutral ground, so it's, across the spectrum of creationism. No matter what little tribe you think yourself a part of, everybody's coming to ICC. And it's very encouraging. And I know you guys just took over. You took over in time to run the 23 conference. It used to be run by a local creationist organization, Creation Science Fellowship in Pittsburgh. And I would say to you, congratulations on an excellent launch, and may your success continue. May God continue to bless the work of the ICC. I was very encouraged by the last one. Paul, any comments on that?
Well, the other thing to say about that is yikes. We're a year away from having to submit proposals, and that's a bit frightening. It doesn't seem all that long since the last conference. Here we are having to think about what we're going to do at the next one.
Yeah.
And we've got to get our skates on, haven't we, Todd?
Well, I've already been thinking about it. So there's part of me that's so excited and so thrilled and just ready to do everything. And then there's this other part of me that thinks you need to do a sensible number of papers and not an insane number of papers.
Mm-hmm. Yes.
Anyway,
I think at the last conference, you have about 5 or 6 papers, and
yes, I did.
yeah.
I did like 6 papers. I was crazy. It was like 50,000 words of research that I presented there. It was bonkers. I might break that this year. We'll see how it goes. I've basically decided I'm not going to do any papers all by myself, that I'm going to always work with collaborators, and a bunch of those collaborators are going to be student collaborators as well. So I will have, I hope, half a dozen different students working with me on projects, which is, that fits what we do at Core Academy. We're all about raising up a new generation of creation scholars. And so, yeah, let's all go to the ICC and we'll all do papers together and it'll be great. And so, but yes, if you're listening and you're thinking, hey, ICC sounds great, I should do that, you should absolutely go out and start thinking about what you're going to do and planning your research projects, getting ready to go, because time's going quick and it will soon be here sooner than you know it. Let's put it that way. Yeah, ICC is coming. So, well, I think we've run out of time for this episode. Flood is not as toxic as you thought, so don't forget what we talked about. But also, ICC is coming, and Aaron, thank you so much. Please convey our excitement and encouragement to the rest of the ICC committee as well. We are ready to go and thrilled. So,
All right, we're looking forward to it.
Yep. Thank you.
Yeah.
And we will be back in 2 weeks. Don't forget to like and subscribe and all that jazz. Visit us at letstalkcreation.org to find out how you can sponsor and help support the work that we're doing. We don't know what's coming up in 2 weeks, as usual, but come back in 2 weeks and find out for another episode of Let's Talk Creation. Thanks for coming.
We'll see you then.
Thanks for listening to this episode of Let's Talk Creation. For more information, visit us at letstalkcreation.org, where you'll find an archive of past episodes and all our show notes. If you'd like to leave a comment or make a suggestion, you can find us on all the major social media platforms. Let's Talk Creation is brought to you in the U.S. by Core Academy of Science and in the U.K. by Biblical Creation Trust. As a listener-supported ministry, we are grateful for all of your financial support. Find out how you can make a contribution at our website, letstalkcreation.org. Also remember to like, subscribe, and share this episode with your friends. Thanks, and see you next time.